Welcome back. Today we'll solve trigonometric equations. Whenever possible, make sure that you're trying to collect like terms, use those algebraic skills like factoring that you've done for the past few years. We always want to isolate the trigonometric functions whenever possible. So try to make sure you bring them to one side and solve the equation that way. So if we have something like 2 times sine of x equals 1, we want to isolate sine of x. So we have sine of x equals 1/2. And then we could look at the unit circle if we want, or think about the quadrants that sine will be positive in. Remember, you're using that all students take calculus. And we know that sine will be positive in the first and the second quadrants. So using that reference angle, using that 30, 60, 90, we know that this angle will be pi over 6. And then we could find the second angle by just subtracting that from pi. And we know that if we're going to include all solutions, well, that this will continuously repeat every 2 pi. So we add 2 pi n at the end. So it'll be pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n to capture all of the solutions. Because we know that this function is going to continue, it's periodic, and every time we make this cycle, we're going to continue to hit that y equals 1/2 twice in one period. Okay, now let's get to the next one. So over here, I'd like you first to try A and B and pause the video, and then we'll come back and we'll check your answer. All right, let's check our answer for letter A. Again, here we're finding all solutions. So remember, we're going to have to include anything else or any of those possible solutions after one period. So considering 2 sine x minus 2, you can isolate that to equal sine of x equals root 2 over 2. Again, we know that sine is going to be positive in the first and the second quadrant. So that's going to be a 45, 45, 90 triangle, and that's going to be pi over 4 plus 2 pi n and 3 pi over 4 plus 2 pi n. Looking at B, well, we can isolate that as well. As soon as we take the square root of both sides, we're going to get plus or minus. So that's going to indicate that we're going to have solutions in every quadrant, right? Because cosine is positive in 2, 1 and 4, and then it's also negative in 2 and 3. So when we capture all of the solutions, you have a couple choices, but we have pi over 6, that's our reference angle in the first quadrant here, because we know that's adjacent sides root 3, hypotenuse is 2. But then when we consider the other angles and the other rotations, well, if I extend this line here, we can actually capture the rotation in quadrant 3. And so we can just add pi n if we want. If we want to include that angle, you could say pi over 6 plus 2 pi n and 7 pi over 6 plus 2 pi n. But you can capture both just with this expression because it repeats every pi n. And then the next one, 5 pi over 6 is in the second quadrant. Again, if you extend that radius or the diameter of the unit circle, you'll get the other rotation, which is 11 pi over 6. So you can say 5 pi over 6 plus 2 pi n, 11 pi over 6 plus 2 pi n, or put them together and have 5 pi over 6 plus pi n. Okay, let's go to the next two. And here we're going to look at factoring these expressions first. So try factoring them, and it's a little bit different, but we're going to find all of the solutions between 0 and 2 pi. Pause the video and come back to check your solution. Okay, let's consider the first problem. So here we have sine of x squared equals 2 sine of x. We have to make sure we get all of the sine of x's to one side, all the trig functions. And then we can factor out a sine of x and then solve. So sine of x equals 0 when x equals 0 and pi. And then for sine of x equals 2, well, remember, sine of x does not go above 1. So we will have no solution on that part of the factor, but we still have 2 solutions that work. For the next one, well, we can factor this into 2 sine of x minus 1 times sine of x minus 1. And then we solve sine of x equals 1/2. Well, that will have the rotations pi over 3 and 2 pi over 3. And then sine of x will equal 1 at pi over 2. Now let's complete example 3. I'd like you to pause the video to complete this, but before you solve it, consider what trig functions or identities that you can use to substitute and make this into one function. And then after you get your solutions, make sure that you're checking for extraneous solutions for anything between 0 and 2 pi. You probably recognized right away that you can use sine squared plus cosine squared equals 1 by squaring both sides. And we can substitute 1 minus sine squared for cosine squared of x right here. Whenever possible, we want to try to make sure we're using one trig function in the equation. Makes our lives a lot easier when solving. So here we can factor that, and we get sine of x equals 0, so 0 and pi, and then sine of x equals -1, which is 3 pi over 2. Now just be careful, because whenever we're squaring, and oftentimes we're going to see this in trig functions as well when solving, we'll probably need to check our solutions. Okay, so oftentimes, especially when we're manipulating the equation, we may introduce a solution that is really an extraneous solution that actually wouldn't work in the original equation. So whenever possible, make sure that you show your work for your checks. So for each one, I just showed what was the solution, or what was the expression when we plugged in each of the values for x. So when we plugged in 0, well, sine of 0 is 0, cosine of 0 is 1, so that's going to work. When we plug in pi, well, sine of pi is 0, but cosine of pi is -1. So that one is actually going to be an extraneous solution, and that will not work. Okay, it worked when we squared both sides, but it won't work for the original equation. And then when we plugged in 3 pi over 2, well, sine of 3 pi over 2 is -1, and cosine of 3 pi over 2 is 0, so 0 will equal 0. So we actually only have 2 solutions. So just making sure we're rewriting this, so we're only going to include 0 and 3 pi over 2 as our final answer. And it's probably helpful to start drawing a box around your final answer, just to be clear. All right, for these next two, again, try these problems for multiple angles. All right, we're finding all the solutions, and then pause your video, and then we'll come back and check your answer. Okay, so here we have sine of 2x equals root 3 over 2. So if I just solve for 2x, well, we know sine of x, regular sine of x, will equal root 3 over 2 at pi over 3 and 2 pi over 3, quadrants 1 and 2. And that would repeat if it was just regular sine of x at 2 pi n. Now let's set this equal to 2x, and we're going to divide both sides, everything on the other side, by 2. So now we know that this will be pi over 6 plus pi n, and pi over 3 plus pi n. And so just remember this 2, which is our b, would change the period. Remember, the period was 2 pi, but we divide by b, which is our 2. So again, this period for this function would be just pi. Now let's look at the second one here. Cosine of x over 2 equals 1/2. So again, if we consider this period here, this would be 2 pi divided by 1/2. So that's really 4 pi. So we can say that cosine would usually equal 1/2 at pi over 3 and 5 pi over 3. When we multiply everything by 2, we get 2 pi over 3 plus 4 pi n, showing that period, and 10 pi over 3 plus 4 pi n. Okay, for these last two problems, we want to use the inverse function. So go ahead and pause the video, try to solve these problems, try to find all the solutions between 0 and 2 pi, and then come back to check your solution. Okay, for the first example, we're going to factor it just like we had for previous problems, but you will notice that we do not have special triangles here. We get tangent of x equals 3/4 and tangent of x equals -2, both of which are perfect solutions, and ratios we can get those values, but of course it'll be a decimal, not a special triangle. So if we're going to solve for x, we just use the inverse function. So we're going to say, all right, let's find the inverse function, and so we're going to say arctangent, or remember you could use inverse tangent, so tangent to the -1. So for the first example, for the first solution, it's going to be arctangent of 3/4. Remember, that's going to put us in the first quadrant. So that answer would just give us a positive number. That's totally fine. But remember, tangent is also positive in the third quadrant. So if we're going to find that angle or that rotation, we'd have to add the reference angle to pi. So it'll be pi plus arctangent of 3/4. Now looking at the next two, we know that tangent is going to be negative in the second and the fourth quadrant. Now what I'd like to do is, if it's tangent of x equals -2, all right, this is going to be a negative. So it's going to have our tangent of 2 as our reference angle, but I'm still going to find those rotations in between 0 and 2 pi. So to find the rotation in the second quadrant, it'll be pi minus my reference angle. Remember, my reference angle is positive, so it'll be pi minus arctangent of 2. And then we have x equals 2 pi minus arctangent of 2 for the fourth quadrant. And you will remember that the even in odd identities, that tangent is odd. So arctangent of -2 is the same as negative arctangent of 2. Okay, let's look at the next one. And let me just box these answers because there are 4 solutions there. Okay, so this is already in factored form. So we get sine of x equals -1/4 and sine of x equals 2/5. So again, for the 2/5, I know that sine is positive in the first and second quadrants. So that's going to be arcsine of 2/5 for the first quadrant here. And then for the second quadrant, that's just going to be pi minus the reference angle. And then looking at the second solution, -1/4, well, that reference angle is going to be just 1/4, arcsine of 1/4. So if I was going to find the rotation in the third quadrant, that'll be pi plus that reference angle, which is arcsine of 1/4. And then in the fourth quadrant, it'll be 2 pi minus arcsine 1/4, because arcsine 1/4, again, was our reference angle. So we do have 4 solutions. And they are not special triangles, but we can use inverse functions to solve for them. Well, I hope this lesson was helpful, and I'll see you all in class.